Hello class. In topic 1.12, transformation of functions, you will learn how to construct a function that is the additive and or multiplicative transformation of another function, meaning that we're going to simply slide something up and down, left and right, or make it wider or skinnier, both either horizontally or vertically. And we're going to go over the different notations so we can distinguish what does what. We're going to start by first looking at vertical transformations. The notation for a vertical transformation is this notation that you see right here, f of x plus k. So we're going to create this new function called g, and it's going to be a result of getting a function f, an existing function f, and adding some value of k. This is resulting in an additive transformation where all of the y values are going to be shifted by this value of k. If k is a positive number, then it shifts up. And if k is a negative number, then it's going to shift down. And we say that this is a vertical translation. So if we look at this value right here, we see that this is the existing function f. And we want to create this new function we'll call g by doing some transformation for it. Now, right now, the domain of this function f are the y values that are greater than this line right here, which is at y equals, let me zoom in, at y equals -3, and less than this highest point right there, which is at the y value of 1. So the range of this function, I'll write it up here, our range are going to be the y values that are less than or equal to 1, but greater than or equal to -3. That's the current range. By creating a vertical transformation, a vertical translation, and shifting this graph up or down, that's going to change the range and move, again, those boundary points where the lowest y value from -3 and the highest y value from +3 to be somewhere else. So let me erase this and keep those values right there. So let's say that the function g is going to be created, and let me do it a different color now that I see it. I want to do it in blue. Let's say g is going to be creating by getting this existing function f and adding, let's say, 7 to it. So what this is going to do, that's going to get every single point from these corners and everything in between and shift the entire function 7 units up. So this would move up 1, 2, 3, 4, 5, 6, 7 to that position there. This would move up 7. 1, 2, 3, 4, 5, 6, 7 to that position there. This point and this point will move up 7. So 1, 2, 3, 4, 5, 6, 7. So here and here. And that will make this function f up. So this right here would be the function of g, this blue function there. And as you see, everything has now been shifted up a total of 7 units. And if I just focus on the vertices, on the corners where the graph changes direction and just connect those dots, then obviously everything else moves along accordingly. So this will be the result of this. And if we look at the domain of g, this new function here, the domain has also shifted. Instead of being the lowest y value being at -3 and the highest y value being at 1, it is now all 7 units higher. The biggest y value is at 8 and the lowest y value is at +4. See, compared to when it was at 1, at y is equal to 1 and y equals to -3. 1 plus 7 is equal to 8, and this lowest point, -3 plus 7, is equal to 4. Now let's say we want to move the graph downwards. So in order to move it downwards, g, we'll do it in a different color this time, we'll do it in green. G will equal to the existing function f, but we'll add a negative number, which is the same thing as basically just subtracting. So let's say I subtract 5. So all these points are now going to be shifted 5 units down. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the same thing over here, 5. And the graph will look like this. So this function again is the same as the previous one. So our our range is from +1, and this value down here is at -3. And you'll notice again, by shifting it down, the range has now shifted to where the highest y value is, I'm going to do it on this side, is at -4, and the lowest y value is -8. Which you can clearly see the y values, and let me zoom in, y equals 1 and y equals -3 are now a difference of 5. 1 minus this 5 is now at -4, and when I get this y value of -3, the lowest y value, which is at -3, and I subtract 5 from it, that moves it to -8. So performing these vertical shifts is going to affect the current range of the function and change it to a new value by simply adding or subtracting whatever this number is, okay, to the current y values that we have here. So we know that the range of this function is this. We can know what the new range would be of this function g by simply adding if it's a positive number and subtracting if it's a negative number to those current y values. Now, let's now look at horizontal translations, shifting things from left to right. Well, the notation to shift something left and right is still going to add. We're going to use a different letter. Instead of K, we're going to say it's going to be H, but now notice where it's located. It's inside the parentheses compared to out here where the K was being added outside the parentheses. So that's the one big difference. The other big difference is that the result of performing this is going to do the opposite operation. The result in the horizontal graph of f is by doing the opposite of whatever this value is here. So instead of adding, we're going to subtract if it's positive, and if it was negative right here, we're going to do the opposite and add, make it a positive h. So for example, okay, and well, before I get into the example, let's talk about what it's going to affect. It's going to affect the domain. Since we're shifting things left and right, the domain is going to change. Right now, the domain of this function, and I'll do it right here in the top, is from this x value of -4 to this x value here of +5. I can see that every point that I plot or that I look on this curve of f is going to have an x value that is always bigger than -4 and smaller than 5. So that's my domain. So my x's are going to be less than 5, but they're going to be greater than -4. So let's see how the domain changes when we shift things horizontally. So let's say I want to shift this horizontally, and I want to create this new function g by adding, let's say I add, let's add not too much, 2, okay, adding 2. Well, when you think of adding, well, no, let's change it because that's not going to be enough to see a difference. Let's say it's 5. No, 4. 4 would have to be the max. So let's say we're adding 4. Here, we would normally think, okay, adding, well, that's going to shift it to the right side. But in fact, it doesn't. With horizontal shifts, it's going to have the opposite effect. And adding is really subtracting. So this is not going to move it to the right, but instead it's going to move it to the left 4 units. So this point here, shifted 4 units to the left, is going to move it all the way to -8. This point right here, moved 4 units to the left, is going to move it to -4, and so on. So 1, 2, 3, 4 would be there, and this point here, 1, 2, 3, 4 would be right there. So the graph will, for g, which is this blue graph right here, will look like this. So this is what the graph of g is. And if you compare the domain of the g to f, notice that the domain of g, I'll do it down here, The furthest point, the furthest x value that this thing has is -8, and the furthest right point that this has in terms of x is +1, which again is a 4-unit difference. And so instead of adding 4 to the x's, if I subtract 4 to these x's right there, 5 minus 4 equals 1, and -4 minus 4 equals -8. So this is the result of a horizontal shift to the left. You add, you write that you're going to add 4, but you're really doing the opposite and subtracting 4 to there. So as a result, if I want to shift something to the right side, also 4 units, the notation will now simply subtract 4. And this is going to move everything to the right by 4. So it would end up adding 4 to those value in our domain. Right now our domain is the same as before. It goes from -4 and +5. Every point between those two values, every point on this graph is going to have an x value that is either -4 or +5 or something in between. No point is going to have an x value that is less than -4 and greater than 4. Now when I graph G, this is going to shift the graph 4 units to the right. So 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. That one right there. So this line, the slanted line, is now here. This line is going to be shifted 4 units to the right. So 1, 2, 3, 4, and 1, 2, 3, 4. That's going to go right here. And then, well, this point is going to also be shifted 4 units to the right. So 1, 2, 3, and then 4 all the way out there. And the graph is going to look like that. And if you look at this, this has changed the domain to 0. All my x values are going to be found between 0 and, well, this one outside here, that's 9, which again is simply -4 plus 4, not -4, is the opposite. Plus 4 is 0, and 5 plus 4 is 9. So there are your horizontal and vertical translations. So let's look at the next page. Now let's talk about vertical dilations and reflections. We'll start with vertical dilations. A vertical dilation is going to multiply again and transform the function by resulting in a vertical dilation of a factor of a. Now, if the value of a is a number less than 0, then it's going to reflect the graph and flip the graph horizontally and have it be upside down. So for example, let's say I have this function again, f, and I want to create this new function g by multiplying the function, the original function, by some number a. If that number a is a positive number, let's say it's +3, then all that's going to happen is that all of these values are going to stretch, and it's going to transform this function by being 3 times its original size in terms of height. So here, this point, instead of going up only 1 unit, is now going to go 3 times as high. So at -4, it's going to go all the way up to 3. 1 times 3. This point right here, instead of going down to -3, it's going to go 3 times as low. So 3 times -3 is -9, and that's going to put that point all the way right there. The x values are not changing, but yet again, the y coordinates are what being affected when I perform this vertical dilation. And the same thing with these 2 points right there. Since these 2 points have a y value of 1, instead of going down only 1 unit downwards, -1, instead of going 1 unit downwards, they're going to go 3 times as many units down. So they're going to go down to -3. And the graph of G will now look like this. So all I am doing when I do a vertical dilation is multiply my my y values by whatever that scalar is, and make it that many times bigger, or make the distance from the x-axis that many times bigger. So instead of only going 1 unit high, like this point only goes 1 unit high above the x-axis, it's now going to go 3 times as high. So 1 times 3 is 3. This point right here, instead of only going 3 units below the x-axis, is going to go 3 times as big. So 3 times 3 is 9, so to -9. And then the same thing with those values there. Now let's say that I'm multiplying by a number that is a negative number. So I want to create this function g, and I'm multiplying by -3 this time. So what's going to happen to this function f is that all the y values are going to be now 3 times further from where they originally are, but because of the negative, it's going to flip them, and it's going to result in a reflection. So in terms of mathematical situation here, all I'm doing arithmetically is multiplying all of these y values to these points here by a -3. So since this point has a y value of 1, 1 times -3 would be -3, and that would move that point to this location right there. Since this point has a y value of -3, -3 times -3, that's +9. So that would move that point all the way up there. So not only is it 3 times away from the x-axis, but also in the opposite direction because of that negative sign there. And the same thing is going to be true with these 2 points. These 2 points have a y value that is equal to -1. Multiplying that y value of -1 with -3, that's going to become +3, and that's going to put those 2 points right there. So the graph is going to look like this. So not only is the graph upside down because of the negative sign, but because of the 3, it's 3 units again. It's 3 times as high as it was, or 3 times as far from the x-axis as it would originally was. Now, if we're doing a horizontal dilation, the same effect is going to happen, just with the x values this time. So as you clearly see right here, we're multiplying, but now the multiplication is with the x's. Now the multiplication transformation of f is a horizontal dilation of the graph of f by a factor of 1 over b. So instead of multiplying by this value of b, we're going to multiply by the reciprocal of that value when we're doing this operation to the x. And if the value of b is a negative number, then it's simply going to reflect it across the y-axis. So for example, so let's say we want to create this function g by getting the existing function f and writing that we want to multiply the x values by 2. Okay, so here we're really not going to multiply the x values by 2. We're going to multiply the x values by the reciprocal of this value. So our x's are actually going to be multiplied by 1 over 2. So to graph this transformation, we're going to look at the current x coordinate. So like this point right here, the current x coordinate is -4. And we're going to multiply that -4 with 1/2 and not 2. So again, by the reciprocal of this value. So multiplying -4 by 1/2, that's going to give us an x value of -2. The y value is going to stay the same, but instead of it being now only 4 units away from the y-axis, it's now only going to be half that distance, 2 units away from the y-axis. Well, in this position right here, our x coordinate for this one is 0, and multiplying 0 with 1/2 is going to keep it at 0, so that one doesn't move. This point right here, this point has an x value of +2, and multiplying that +2 with 1/2 is 1, so I was going to put that position right there. And then this point over here, that x value is 5, and multiplying 5 with 1/2, that's 2.5. So that's going to put that point right here at 2.5. Notice that the y values did not change. The y value stayed the same here when we did this type of transformation. And then of course the same thing would be true if I was doing this in the opposite order. Let's say let's say I had this other function, we'll do it in red, called h of x. And I was going to create h of x by multiplying the x values of f by 1/2. Well, here I'm not really multiplying the x values by 1/2. I'm multiplying the x values by the reciprocal of 1/2, which is 2/1. So I'm multiplying all the x's by 2. So if I look at the coordinates of f and look at the x values of each corner of each point, this point the x value is -4, so multiplying that -4 with 2, not 1/2 but with 2, the reciprocal of that, that's going to move the point all the way up there. This point is going to stay the same place because this one has an x value of 0, and 0 times 2 or 0 times 1/2, that's going to stay as 0. So that doesn't move that point for this nor for that notation. But this point right here on f, which we had a point right here at 2, -1, the x value being at 2, is now going to be twice as far away from the y-axis, because 2 times 2 is 4. And 5 times 2 is 10. So that would move it way out there. And the graph of h, which is this graph right here in red, would look like this. Now, if the number is a negative number, what it's going to do is reflect it across the y-axis. So it's going to flip it across this line right here that I'm going to highlight. So these points get flipped over here, and these points get flipped over there. The x's are simply just going to be the opposite. So let's do something simple. Let's do that g of x will equal to f of -x. We're not going to multiply it by anything other than -1. So what this notation is going to do is simply now multiply all of the x's by -1. And this one is simple because the reciprocal of -1 is still -1. So we don't have to worry about flipping that number, because it looks the same way. So that would mean that this point, -4,1, would be at +4,1. 0, 0 would still be there because, again, the x value at this point is 0. And multiplying 0 with a negative is still going to be 0. So that point still is at the same position right there. Flipping this point changes the x value from +2 to -2. And flipping this point, 5, where the x value is 5, and multiplying by a -1 is going to flip it to the other side to -5. So as you see, the graph simply flipped across and is now pointing in the opposite direction. So all the x values are now over here, and these points, the x values are now over there. The y value does not change because we're not performing any operation to the x coordinates. So let's review and let's recap again these tips, important tips and notes for graphing transformations. First of all, as you saw, any transformation that affects the x values are inside the parentheses, okay? They are inside the parentheses with the variable x. And the transformations have the opposite effect of what it looks like it's happening to the x values. So we have that f of x plus 3. We're not really adding 3 to the x's. We're subtracting 3 to the x's. And if it's f of 3 times x, we're really not multiplying by 3. We're multiplying by 1/3, which is dividing by 3. Multiplying by the reciprocal is just simply dividing by that value. But we're going to stick with the term of multiplying. So we're going to multiply by the reciprocal of that. The only thing that really doesn't change is the negative sign. If I'm multiplying by negative, because the reciprocal of 1 is 1, it looks the same way, where it's 1 on the top and 1 on the bottom. Flipping that looks the exact same way. it looks again like we're doing exactly that. But technically, we are doing the opposite effect of what is written in the notation. Now, any transformation that is on the outside is going to affect the y values of the graph. And those do the exact notation as indicated. So if I'm adding, I'm going to add to the y's. If I'm subtracting, I'm going to subtract to the y's. And the same thing with multiplication. Now, additive and multiplication transformations can be combined, resulting in the combination of a horizontal and vertical translation and dilation. And the way that these are done is by performing, again, these operations following essentially your order of operation. So if I want to transform this function, here I have this function f, all right? So this is the graph as f of indicated. And the graph of f exists by connecting two line segments. So this line segment and this line segment here, and a semicircle, this semicircle right there. And it's shown to exist between -4 and -3. You see -4 and -3 for your x values. We want to sketch the graph of this new function we're going to call k by performing this operations to the function f. So let's take it one at a time. Well, because of order operation, well, our order operation, if this was again like numbers, like if we had -2 times x minus 2 plus 1, ignore that the f wasn't there and just had this. The order of operation, if this value of x was some number, let's say 7, would first require us to simplify the inside part first before I can multiply it with the -2 and then add it with the 1. Well, I'm going to do the exact same thing with these transformations. I'm going to first focus on the inside of the parentheses first and see that's how that's affecting the x values. Okay, so well, let me make my order, a table of the current x and y values to f. So right now, let's start with the points again at the vertices of this line segment here. So this line segment has an x value of has a coordinate of -4, +1, and it's connected to this point here where the x and y value are -2 and +1. Now, I'm not going to get every single point on this circle here. I'm just going to focus on this point right there because it's going to be an arch. So I'm just going to do my best to connect this arch in the correct slope or the same curvature, and the same with this one. So I'm just going to focus on this point right there where that point is at 0, -1. Then the same thing with this point up here on this line segment. I'm just going to focus on, again, the ends of that line segment. So 2, 1, and 3, -3. So here, this is the x and y values to this part right there. We want to transform it by doing this. Well, let's start with, like I said, on the inside. Well, here it noted that x is going to be subtracted by 2, but really we're not going to do that because anytime we do these transformations on the x, the opposite effect is going to occur. -2 doesn't mean to move it to the left. It means to move it to the right. In order to move to the right 2 units, all my x coordinates are going to increase by 2. So if I want to perform this operation where I'm going to move to the right 2 units, I'm going to create a new table. And let me highlight it. Let me do highlight here. So to do this part, this is going to create a new table where the x values and only the x values are going to change by increasing by 2. So -4 is now going to be -2. -2 plus 2 is 0. 0 plus 2 is 2. 2 plus 2 is 4. And 3 plus 2 is 5. My y values have not changed, at least not yet. Okay, because all I'm doing is focusing on this. Now that I'm done there, the order of operations puts multiplication before addition. So I would have to multiply all my y values because it's on the outside. That's going to affect the y coordinates, and multiply them all by -2. So I'm going to multiply all of these y values by -2. So I'm now doing this. So let me write a new table using green. So all my x values are going to stay the same, -2, 0, 2, 4, and 5. And all my y values are not going to be negative 2 times what they originally are. So 1 times negative 2 is negative 2. Negative 1 times negative 2 is positive 2. This is negative 2 again. And negative 3 times negative 2 is positive 6. And then finally, the last transformation I have is this plus 1. Well, this plus 1, because it's on the outside, is going to affect, yet again, the y coordinates. And it's going to do exactly as it says to the y coordinates. It's going to add 1 to all of the current y coordinates. So since this is the last transformation I did here, okay, since this is the last transformation I did, I'm going to now, again, transform those by adding 1 to all of those y values. So the new table I'm going to end up creating, doing this purple transformation, is going to keep the x values the same and add 1 to all the y values. So 7. Okay, negative 2 plus 1 is negative 1. 2 plus 1 is 3, and so on. So let's plot those points. Okay, so now that I have all the transformations done, I now have the table for this function k. So here we plot the point negative 2, negative 1, 0, negative 1, 2, 3, 4, negative 1, and 5, 7, which is right there. So these two connect with a line segment. The next 3 points are supposed to be an arc, a semicircle, so they should connect again with somewhat of a semicircle feature. And then the last 2 points are connected with a line segment. So this is what the graph will look like. Let's look at now example 2. So example 2, we have the exact same function. We now want to do a different transformation. So just like the previous, we want to start with the inside first. And notice that there's 2 set of parentheses there. We always want to do the horizontal shifts before we do any other thing. So because this one does have a horizontal shift, we're going to perform this operation first. So our x values are the same as above, so I'm just going to copy this. Let's see, let's duplicate that and move it down here. Okay, it's the exact same picture as above, so the x values and y values start off at the same thing. And I want to first perform this, the horizontal shift. Well, minus 2 is not really going to move it to the left. It's going to do the opposite operation and move it to the right, just like last time. So all my x's are going to be the 2 units higher. So negative 2, 0, 2, 4, and 5. Now I have a multiplication again, but this time the multiplication is on the inside of my parentheses. Here's my function f, so it's on the inside of the parentheses of this function f. And because of that, it's gonna affect the x values. But instead of multiplying the x values by 2, we're going to multiply the x values by the reciprocal of 2, which is 1 over 2. So this notation means to multiply the x's by half of, and not 2 over 1. So here the y values are the same. I didn't write them because they didn't change because of the 2 things that I've done, so they're the same. But when I do this new transformation, that's going to affect the x's again. So my y values are going to be the same. Let me write those before I forget. And we're going to multiply all of our x's by half. So half of negative 2 is negative 1. Half of 0 is still 0. Half of 2 is 1. Half of 4 is 2. And half of 5 is 5 over 2, or 2.5. And then finally, the last transformation I have is on the outside. So that's plus 1, and that's going to affect the y coordinates by adding 1 to all those current y coordinates I have from the red table. So my x's are not going to change. but my y values are not going to be one unit higher. So 2, 2, 0, 2, and negative 2. So let's plot it and let's see what this graph is going to look like now. So negative 1, 2 is here. 0, 2 is there. 1, 0, 2, 2, and 2.5 and negative 2 right there. 2.5 is there. So connecting these two, connecting these with what should look like a semicircle, and then connecting these two with a line segment will make the graph look like that. So as you see, again, the key thing in doing these multiple transformations is to work within the inside first. Start with your horizontal shift, any horizontal dilation, and then do the vertical affects the y's. Okay, so start with the x transformations and how the x values are going to change, and then work your way outside by then doing the multiplication of the y, and then if there's any addition, do any addition to the y. And we didn't do any multiplications to the y because we were not multiplying anything on the outside of this function f. So it's understanding again that this is just a notation that we have this function f right here, and we're going to create this new function p by multiplying the x value to our f by 2, subtracting 2 to the x value to, again, this function f, and then adding 1 to the entire function f, which affects the y values. Okay, now let's talk about how do we evaluate a function which is the result of transforming another one. There's two options. I can create a new table just like I created a new graph here by seeing how this function is going to be transformed by this notation here. And now we'll create a new table of x and y values from this current function p. So let's do it that way first. So here, before I can figure out what h of negative 1 is, I have to figure out what's going to be the new table for x and the new table for y for this function h. So let's start first with the x coordinates on the inside. As you see right here, our x values, p again is just the name of the function, but our x values are being multiplied by 2. Since it says that we're multiplying by 2, we're really not multiplying by 2, but we're multiplying by the reciprocal. So we're going to multiply our x's by 1/2. So getting half of all of these numbers would make this x values negative 1, 0, positive 1, positive 4, and positive 3. Now the outside values that we see here, this 3, means that we're multiplying the y values by 3. So we'll multiply all of these y values by 3. And I'm going to write it right here because I don't want to, I want to write the final answer here. So I want to write the final answer here. So I'm going to write the new numbers right there underneath right here. So I'm going to multiply all of these numbers by 3. So 3, 0, 9, and 7 times 3 is 21. Okay, so that's that right there. And as you see, we still have one more operation. We have this -1, but it's on the outside of the parentheses of p of x. So that's going to affect the y values yet again. And all of these new y values that are in purple are going to now be subtracted by 1. So here's going to be the actual final y values for h. 3 minus 1 is 2. This is going to be -1, this will be -4. -1, oh, that should be a negative right there. 9 minus 1 is 8, and 21 minus 1 is 20. Okay, so now that we have this new table represents the x values to this function h and the y values to, again, this function h. So if I want to know what is the y value when x is -1, I look at the new table, find where x is -1, and the corresponding value there is 2. So there's your answer. Now, there is another method you can apply here that to me, I find a lot easier. Since we're trying to evaluate this notation of h when x is -1, I can use direct substitution. Since h of x is equal to 3 times p of 2x, 2 times the value of x, minus 1, like I mentioned, you can use direct substitution. So I'm going to replace this x right here with the value that I want for h, -1. So as you see right here, that's where I put the little space right there, because I'm going to multiply 2 times the value of x, which is going to be -1. And I can simplify that expression right there. So let's substitute in that value. So I'm going to plug in -1 right there, okay? So we have 3 times p of, well, 2 times -1 is -2 minus 1. Now this notation right here, p of -2 as the way it's read, p of -2 as we read this right there, can be found in the original table. Let me erase all this, okay? In the original table, this means that we're looking for the y value when the x is -2 for the function p. So right here, when x is -2, your y value is 1. So I can use that direct substitution and replace this with this number of 1, which then changes the expression to 3 times 1 minus 1. And well, look at the math. 3 times 1 is 3, and 3 minus 1 equals 2. The same value that I got by just doing that direct substitution from the very beginning. So instead of going through the trouble of creating this entire new table here and doing essentially what we did up here, but in terms of just the table part and not the graphing part aspect of it, I can evaluate a function h, which is the result of transforming another function p, by using just simply direct substitution. So here we can figure out what h of 2 is, okay, by doing again this simple technique of direct substitution. Instead of like I said, instead of going through all of this trouble to create this new table, I can just simply do direct substitution. So first of all, h of x, let me rewrite that. H of x is 3 times the function of p of the value of 2 times the value of x minus 1. And since we're going to evaluate this function h when x is 2, that means I'm going to replace this x with the number 2. So it would be 3 times p of 4, since 2 times 2 is 4, minus 1. I can now look at my table, my original table right here, look for where x is 4 right here, and see that the y value is 3. So p of 4 equals to 3, and I could do that substitution, replace this with 3. So 3 times 3 minus 1, well, that's a total of 9 minus 1, which is 8. So there's your answer. H of 2 equals to the value of 8. So, and to me, I find that a lot easier and more convenient than having to create this new table by performing the set operations and then finding what the y value is at that given value that they want here. And then finally, one last thing I want to go over again just one more time, the domain. How is the domain and range affected by resulting in new, again, transformations? So here we have q of x, and which is the domain and the range of a function n is from -6 to 9, and the range is from -8 to 10 respectively. So domain, let me highlight this. I'm going to highlight the domain in blue and the range in red. Okay, so domain is in blue and our range is in red. Now additionally, n is increasing on the intervals and decreasing on the intervals 1, 5. So it's going up from -6 to 1 and 5 to 9, and the graph is going down from 1 to 5. So let's see how the domain of Q is going to be, what the domain of Q is going to be by transforming this function. So let's clean up, first of all, the notation here. Let's write this, first of all, as -2 times the function n of negative x plus 5. And then we have the plus 4 in the back instead of having it right here in the front. So all I did was just rearrange this and rewrite this so it looks like this. So here's our function, and we are doing two things to the x's, multiplying it by a negative and adding 5. Well, not really adding 5, but subtracting 5. So let's see how this function is going to change. And I want to do one other thing here. I want to factor out the negative so I know that the direction is going in the right way. So let's factor out the negative. So we're going to write this as x minus 5 and plus 4. Well, again, the domain is affected by seeing what's happening to the x's. We're doing two things to the x's. First thing, again, we work with the horizontal shift. Minus 5 is really adding 5. So our x values, which is our domain, we're going to add 5 to those two numbers. So that's going to be -1, and adding 5 to 9, that's going to be 14. But since we're also multiplying, that means we're going to multiply those x values, these current x values, by that negative sign. So that's going to change the 1 to a -1, and that's going to change the 14 to -14. Positive 1, I'm sorry, not -1, positive 1. So this is going to be the domain. This is going to be the domain for this function Q, I'm sorry, for this function Q. So by performing the horizontal transformation, that's going to affect the current domain to those values there. And well, the range is going to be affected by performing the operations to the y values. The operations we're performing to the y are on the outside. We're doing two things. We're multiplying and adding. Well, because we're performing these operations to the y, this one actually follows the order of operations, and we do the multiplication first before we do the addition. When it comes to the horizontal, we do everything backwards. We do addition, or in this case subtraction, which is really addition. Again, we do the addition of 5 first and then the multiplication. But for the y values, because the notations are on the outside, we do multiplication first and then the addition second. So we're going to multiply these y values. I'm going to do it in one step. We're going to multiply these y values by -2 and then add 4. So if I do that to the -8 first, -8 times 2 is 16, and then plus 4, that would be 20. Multiplying 10 with -2, that's -20, and then plus 4, that's -16. So this is where the range is going to be now for Q. Let's now look at part B. On what intervals is Q going to increase or decrease? Well, we know that N is increasing on the interval. Let me highlight it in purple. It's increasing on the interval from -6 to 1 and 5 to 9. Remember, these are x values. x1 to x2 and x1 to x2. And it's decreasing on the interval from 1 to 5. Oh, I do have to make a correction on the range here. The notation for the range should not be closed brackets here. This one right here should be parentheses. Okay, parentheses, because it is open on that one. Oh, on the sorry, this is the wrong one. And I also need to fix again the order of my interval, because my interval doesn't make sense. My interval for the domain is incorrect because it should be from -14 to 1, and the range, oh, why did I erase it? Oh, let me go back. Okay. The correct interval is from -14 to 1, and that's going to be bracket on both of them, since it was bracket up here. And on this, the same thing is going to occur. I have to write this again in the right order. The smaller number, remember, always goes first. So it's going to be -16 and +20. And since the negative 16 was open because of the shift right here, this was open, this is going to still be open, and the 20 is going to be closed. So correction on the answer for A. So let me go now let me go back to letter B, and let's figure out where the function is increasing and decreasing. Like I was stating, the function is increasing on the interval from -6 to 1, 5 to 9, and it's decreasing from 1 to 5. So because of the horizontal shift, that's going to move those points to, that's going to move the points to 5 units to the right. So -1, 6 would be the first interval. This interval right here would be that one. This second interval shifted to the right by 5 would be 10 and 14. And an interval where the function is decreasing, again, a shift of 5 units to the right, that would be 6 and 10. Now the negative sign right here is going to flip the graph across the y-axis. So all my x's are going to be the opposite. So this would be positive, this would be negative, 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 and negative. So if I put these intervals in order, that would be from -6 to +1, -14 to -10, and -10 to -6. And this is where the function is increasing, and this is where the function is decreasing. And that's all because of the horizontal shift and the reflection. Now, normally these would also be the opposite. Since I am reflecting it across the x-axis, the intervals where the function is increasing should be now decreasing because the graph is going to be pointing in the opposite direction. So for example, look, let's say I have an x and y axis. So I have my, let me do it in black, and let me do it a different color so we could see this. There we go. So here's my y-axis, here's my x-axis, okay? And let's say I'm increasing from this point to this point. So let's say I'm increasing from 1 to 4. If all I do is shift, okay, and all I do is move this 5 units to the left, this is going to move, to the right, 5 units to the right, this is going to move to 6, and this is going to move to 10. But the graph is still going to be increasing, still going to be pointing upwards. But when I multiply that x value by a negative, that's going to flip across this y-axis. So this point flipped across the y-axis, we'll put it right here, from +1 to -1. And this point over here flipped across the y-axis by multiplying again the x by a negative. We'll flip this point and make the x from a +4 to a -4. But the y values are still going to stay the same. So the graph will look like this. So you see, instead of increasing from -4 to 1, it's actually now decreasing because of the negative value. So the intervals are going to change. So this should technically be decreasing, and the same thing right here. This should technically be decreasing because it was originally increasing. So this should be now going down. But since I'm also performing a vertical translation, and I'm multiplying the vertical reflection, and I'm multiplying the y values by a negative number also, that's going to flip the graph upside down. So this point, by this negative sign right here, that's going to flip this point across here and this point down there. So by looking at that and flipping it across the x-axis, okay, and looking at this graph right here, I see that this graph down here is in fact increasing, is going up. So the two negative signs basically cancel each other out. And if all I do is focus is on the horizontal shift of 5 units to the right, then it's going to keep the same intervals as increasing, and that one interval is still going to decrease. It's just been shifted to the right by 5 units and reflected across the x-axis. So we do have to do the multiplication to the x values, to all those x values, to figure out what the new interval is. But in terms of the direction that the graph is moving, the two negative signs cancel each other out, and the graph is still moving upwards, just like this part is right here. but it's only going to simply be on this side of the x-axis of the y-axis. I'm sorry, on this side of the y-axis instead of being on the other side of the y-axis. So, and the same thing's going to be true on with these points right there. Okay. So if I see again that I'm increasing from 5 to 9, so I should use that point instead. 5 to 9, and all I did was shift it 5 units to the right. Well, it would be 10 to 14, and the graph would still be pointing in the opposite direction. But this negative sign flips it and makes it go down from negative 9 to negative 5. But because we're going to flip it yet again on the outside and multiply by negative and flip it one more time downwards, that's going to put this point up here and this point down there. So it's still increasing. So the intervals do not change because it's increasing. Had there only been one negative sign, whether one negative sign on the outside or one negative sign on the inside, then it would change. These intervals would be now decreasing, and this one interval will now be increasing. It would change. And there. Okay, so that concludes our notes for topic transformation, which is on 1.12, yeah, transformation of functions. Sorry, I was trying to get to the top part. 1.12, transformation of functions. If you have any questions, please do not hesitate to email me or send me a message on Parent Square. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.